In this section, we'll take a look at the MPLS concepts objective of the JNCIS Service Provider exam. We'll examine basic MPLS operation, LDP, RSVP, CSPF, and routing table integration. For more detailed coverage of this objective and more, please check out the Juniper MPLS Fundamentals course.
In this video, we're going to take a high-level overview look at MPLS, or multi-protocol label switching. So MPLS was originally designed for data plane efficiency. The intention is to use a shim header. So this is a header that we insert between the outer layer 2 header, in this case an Ethernet header, and the inner IP packet. And what we're doing is we're inserting this MPLS header between the Ethernet header and the IP packet. And the efficiency gains come from the fact that we're forwarding on a 20-bit label value within the MPLS header instead of a 32-bit destination IP address inside the IP header of the IP packet. Now, the advancement of the chips used in router data planes quickly made this use case for MPLS obsolete. However, in the meantime, the use of this shim header has been discovered to provide a lot of other benefits, and these benefits I've outlined on the bottom left-hand side of the board. And we'll talk through these later on in this video. However, let's first just quickly take a look at the other fields in the MPLS header. So along with this label value, we also have what was previously known as the EXP or experimental bits that have now been renamed as the traffic class bits. And this is what we're using for quality of service marking. We then have the stack bit, and this is used for stacking labels so that we can have more than one label present on a packet. And we can use these different labels for different purposes. We'll examine this in the future a little bit later on in this video and also in subsequent videos. And then finally, we have the TTL field, the time to live field, which is performing the same purpose as the TTL field in the IP header, i.e. we're preventing the consumption of bandwidth when routing loops exist within a network. So now that we've taken a look at the MPLS header in a little bit more detail, let's examine some of the benefits that the use of this MPLS shim header brings to a service provider environment. So first off, we have this separation of forwarding decision from the encapsulated packet. So this brings a number of benefits. The first is that we can run a multi-service network. So we can have things like layer 3 services and layer 2 services running across a common core network, because we're inserting this MPLS header between the encapsulated packet or frame, and we're forwarding on the label rather than the details within the encapsulated packet or frame. So it means that we can be running different services across the same common core. And this gives us statistical multiplex gains. It means that we can get the most out of our deployed bandwidth. This use of a label for forwarding also means that we can do things like traffic engineering. And I've drawn up a little example diagram on the board here to better illustrate traffic engineering. So say that we're looking at the network from the perspective of R1. There are upstream routers, and they are sending traffic to R1, and all of the traffic that these upstream routers are sending is destined to R2. Router 1 has multiple paths through the network, and he wants to send traffic from source X across one path and from source Y across another path. With purely destination IP-based routing, there's no way that he can do this, short of very complicated and very brittle policy-based routing configured specifically on himself, and that can easily fail in very, very strange ways and be hard to troubleshoot. So if we separate the forwarding from destination IP, and instead we're forwarding on this label value, we can establish arbitrary label switch paths through our network using different parts of that network infrastructure. So we can have a label switch path from source X to router 2 using this uppermost path, and we can have a separate label switch path between source Y and router 2 using this bottommost path through the network. And this gives us things like bandwidth efficiency gains in the network, and it means that we can pin different services that have different requirements to links that have different physical characteristics, things like latency and the amount of capacity that they have available. We've talked a little bit about it previously, but with the MPLS header we can also support label stacking. So we can have multiple labels within a packet, and we can have those labels perform different functionality depending on where in the stack they sit. The outermost label can be used for forwarding decisions within the network to get us to a destination router. The label inside of that can then be used for multi-tenancy. We can have segregated routing tables on this destination device, and this label can indicate to which routing table this packet should then be forwarded. This allows us to deploy things like MPLS VPNs. And finally, we can have core routers forwarding purely on the label value of a packet, not the destination IP address of the packet. What this means is that we can remove a significant amount of routing state within the core of our network. We only need our core routers to be learning label values from upstream and downstream routers. Our core routers don't need to be speaking BGP and learning hundreds of thousands, maybe millions of routes from the edge of the network. So it means that we can reduce the amount of state that we need to store in our core routers, in their data plane and their control plane. So it means that we can build routers that are efficient on pushing huge volumes of packets and not necessarily as efficient as storing huge amounts of state, the kind of state that we need to have on the edge of our network. So that was a quick overview of these different advantages that MPLS bring to service provider environments. And we'll explore some of these in more detail in the subsequent videos. In this video, we're going to examine some basic MPLS terminology and MPLS packet forwarding. And to do this, we're going to follow this diagram on the right-hand side of the board, where we have a purely IP-speaking router X sending packets to a destination behind another pure IP-speaking router Z via an intermediary MPLS network. And this intermediary MPLS network spans from R1 through R2, R3, and ends on R4. So first off, let's examine some terminology within the MPLS portion of this network. We have an LSP, a label switched path, running from R1 to R4 that's going to be carrying our packets from X to Z. And the routers that are facilitating this label switched path are called label switched routers, or LSRs. We have an ingress LSR at the head end of the LSP. We have pure LSRs in the middle of the LSP, and at the end of the LSP we have an egress LSR, an ELSR. And in terms of forwarding, the ingress LSR is taking an IP packet and pushing a label onto it. The LSRs are performing pure label switching, and the egress LSR is then performing the IP forwarding onto the end destination. You might have come across some other vendor terminology that describe the elements within an MPLS network. This other vendor terminology would be that the pure IP speaking routers are CEs, or customer edge routers. The ingress LSR and egress LSR can be known as PE routers, provider edge routers, and the pure LSRs, the pure label switched routers, can be known as P routers or provider routers. So with all this terminology analysed, let's now take an in-depth look at how a packet flows from router X to router Z. So router X is sending a packet with a destination IP address of A.B.C.D, and this packet arrives on R1. So R1 does a lookup for this IP address, and he resolves the next hop of the route that covers this IP address in the routing table inet.3. And we'll take a look at this routing table in a little bit more detail in subsequent videos. But the key thing to note here is that the resolution in this inet.3 table gives us a label value and a egress interface pointing at router 2. So what router 1 does when it's found this entry in inet.3 is he pushes a label of L1 and he forwards this packet out of the interface facing R2. On R2, he receives this packet with a label value of L1, and he does a lookup in a different routing table in MPLS.0 for this label value, this L1 value. And in this MPLS.0 table, he sees that there is a swap action for a different label. So what he does is he removes this L1 label, he swaps it for an L2 label, and again he has a forwarding action of sending this labeled packet to the interface facing R3. And this packet, now with label 2, arrives at R3, and R3, although it's a pure label switch router, it's a special label switch router in that it's the penultimate label switched router before we reach the egress label switched router, the ELSR. And on the penultimate label switched routers, in the vast majority of cases, we're going to be performing an action called penultimate hop popping. What this means is that we're removing the outer label on the packet before sending it to the egress LSR. And this is exactly what this R3 router is doing. He's looking again in the MPLS.0 table for the label value L2 on the packet that he's received. He sees the action pop, so he's removing that label, and then he's forwarding this IP packet via the interface facing R4 to R4. And then R4 does pure IP routing on that exposed packet to the router Z, who then has the network containing A.B.C.D directly connected. So he forwards that packet onward to that host in that network. So it's worth spending a little bit more time here explaining why we're doing this penultimate hop popping. And this was an efficiency built into MPLS in the very early days of its development. And let's examine what happens if we don't have penultimate hop popping. So we have the ingress LSR looking up for the IP packet, he's pushing a label, and then we swap, and then we swap again, and then we send that packet with a label value on it onto R4. Now R4 is the end of the LSP. Now he has to perform two actions. He has to remove the outer label, and then he has to perform a second lookup to see what the encapsulated packet is going to tell him what to do, how to forward that packet. And this double lookup process on the egress LSR is expensive. So this is why this penultimate hop popping optimization was built into MPLS. And this is why you see this pop action on penultimate LSRs within the path of a LSP. And we're going to talk about in detail how we signal which labels to use on a given router in subsequent videos, focusing on LDP and RSVP, for how these label values are advertised and signaled. When we're advertising and signaling an action of penultimate hot popping, we use a special label value, a reserved label value of 3. If we didn't want to perform penultimate hot popping, we wanted to get the packet still with a label to our egress LSR, then we would advertise a reserved label of 4. So these values, 3 are what's called implicit null, and 4 is what's called explicit null. And the reasons that you might want to retain that label value at the egress LSR, sacrificing that optimization so that you are still performing a double lookup, are for purposes such like, say that we are using the EXP, the traffic class marking in the labels to perform quality of service classification. We want to retain this marking end to end. So we want to retain the presence of a label end to end on an LSP. That's one of the reasons why you might want to retain end-to-end marking and sacrifice the optimization that penultimate hot popping gives you. So this was a quick overview of the typical forwarding actions that you might see in the path of a label switch path. As I said, in subsequent videos, we'll analyze in detail how different label advertisement protocols advertise these label values to the various routers in the path of LSPs. In this video, we're going to take a look at LDP, or Label Distribution Protocol. Now, LDP is very simple to configure. However, it does lack some of the advanced traffic engineering capabilities of protocols like RSVP-TE or Spring. So let's first look at how LDP establishes sessions from router to router. This is what we have on the left-hand side of the board. So all you need to do to enable LDP, you're enabling MPLS on the interfaces that you want to run LDP over, and you're specifying those interfaces under protocols LDP. We haven't specified any IP addressing in this, and so the first stage of LDP session establishment is called basic discovery, and we're using a multicast address of 224.0.0.2, and we're using the UDP protocol port 646. And this discovery process allows routers that are enabled for LDP to discover each other and to discover each other's IPs. So this basic discovery process goes on, and we find out the IP addresses of our immediate most LDP neighbors. There is an alternative to this basic discovery process, which is to use the extended discovery process, which is where we have specified an explicit IP address rather than using a multicast address. We use this extended discovery process to support targeted LDP, TLDP, and this is where we are explicitly specifying LDP endpoints with IP addressing in the configuration. So with our endpoints discovered using UDP, we then establish a TCP session between those two IP endpoints over TCP, again using the same port of 646. With that TCP session established, we then exchange LDP specific messages, and we perform session initialization to establish that LDP session between two routers. Once that session is established, we can then get down to the process of exchanging labels over those sessions. And the label exchange process is what I've illustrated on the right-hand side of the board. So before we get on to analysing the flow of labels, it's worth highlighting a point of terminology. Within LDP, we have the concept of a FEC, an FEC, or a forwarding equivalence class. And what this is it's a set of destinations that share the same common forwarding. So it would be a group of IP destinations that sit behind the same egress LSR, for example. so that we're forwarding packets to all of those destinations via exactly the same path through the MPLS portion of the network. And you can think of this as loosely equivalent to a label value in LDP. So thinking about label values now, how do we establish LSPs using labels within LDP? So we have an MPLS network consisting of routers R1 through R5. And we're going to be looking at the establishment of LSPs from the perspective of R4 initiating the label advertisement. So with Juniper routers by default, with LDP, we are only going to be advertising a label value for the loopback IP address of our routers. This is because we're going to be having BGP sessions associated with those loopbacks. So we're going to be doing our next hop resolution for routes carried in BGP against our loopbacks. So we probably don't need any other label to IP advertisement going on from our egress LSRs. However, if you wanted to advertise more label to IP bindings than just purely the loopback address alone, we can do this in LDP using egress policies. But that said, for now let's just stick to advertising one label. So R4 advertises a label binding for its loopback address, and he advertises this label upstream to R3. R3 receives this label advertisement, and he creates a local forwarding entry for this label pointing to R4. He then, using a local pool of labels, generates locally significant labels and advertises them upstream to R2 and R5. On R2 and R5, again we're creating forwarding entries for those labels that have been advertised by R3, and we're installing those in our forwarding plane. We're then using our local pool of labels and advertising those upstream if there are more upstream routers. And through this process, what we end up doing is we end up creating a full mesh of LSPs from every router in the network to the initial advertising router. In this case, that's R4. So we've got LSPs running from R1, R2, R3 and R5 all the way through to R4. And this is what LDP is doing. It's essentially creating a full mesh of LSPs to the downstream router. Because the label advertisement is initiated by the downstream router, and we're doing it to all upstream routers, this process is called downstream unsolicited label advertisement. I mentioned earlier that if we wanted to advertise more labels than just for the loopback alone on the egress device, we would use an egress policy. If on any of the upstream devices we want to filter these advertisements, either on receipt or on onwards advertisement, then we can use import and export policies in LDP, much like you can use import and export policy in other routing protocols. This is a quick overview of the functionality of LDP. In this video, we're going to take a look at RSVP signaling. So RSVP supports a lot of advanced traffic engineering capabilities, and we'll examine how you can realize some of those capabilities in subsequent videos. But for now, we're just going to focus on how we can use RSVP to signal LSPs. So RSVP uses its own IP protocol of 46. If you contrast this to LDP that uses UDP and TCP to support its signaling. And within this IP protocol, we have two main message types that facilitate the signaling of RSVP LSPs. We have path messages that flow downstream from ingress LSR to egress LSR, and we have reserve messages that flow upstream from egress LSR to ingress LSR. The path messages request that resources are allocated on the routers that they traverse through, and they also request that a label be allocated and that label be associated with the resources that they have requested. When the path message reaches the egress LSR, resources are allocated on the egress LSR, but we also trigger the sending of a reserve message. The reserve message then flows back upstream, following exactly the same path through the network that the path message has taken flowing downstream, and the reserve message flowing upstream finalizes the allocation of these resources that were requested by the path message, and it also allocates the labels that were requested in the path message. And we allocate a locally significant label on every hop, and that label is then advertised upstream all the way up to the ingress LSR. Contained within these path and reserve messages are objects. So objects are a way that data is structured within these messages. And on the board we have some example objects listed. This is not a conclusive list of all of the objects involved in RSVP signaling, but it's enough to give you a general idea of how the protocol operates. Some of these objects you can find in both messages. So these are things like the session object, which is a unique number that identifies a particular LSP. We have the RRO, which is the record route object, which records all of the routers that a particular message has passed through. And then we have the RSVP hop object. The RSVP hop object notes the previous router that has processed this message. So in this example here, if we have a path message sent from R1 to R2, the RSVP hop message is going to be equal to R1. So those are objects that we see in both message types. In path messages only, we see label request objects. So these are what's requesting that labels be allocated, and that's what's later going to be signaled in the reserve message coming in the opposite direction. We have the explicit route object. Now this is quite closely associated with the record route object, and it is a list of IP addresses that the path message has to traverse through in the network on its way to the egress LSR. And it's in effect a way of specifying the exact path that an LSP must take through the network. If we control where the path message flows through, we control where the soft state is set up, and we also then control where the reserve message flows through on return, thereby creating an LSP on a specific path through the network. And then finally we have the tspec object. So this is an object that's used for requesting that bandwidth resources be allocated as the path message flows downstream through the network. And so now if we look at reserve messages only, we have the label object. So this is the object that's carrying the label that was requested by the path message, and it's what we're actually going to be using for forwarding traffic along that LSP at a later date. And these are locally significant labels allocated and advertised upstream on every device as those devices process those reserve messages. And then finally we have the style object. Generally this is going to be one of two values, either fixed filter or shared explicit. And this refers to how resources are allocated amongst paths that belong to the same common LSP. And we'll take a look at this in more detail in a subsequent video. So that was the objects that we see in these messages. To finish, there are some other messages that are used in error handling and resource teardown, and these are the tear messages and the error messages. So there are both path tear and reserve tear messages, and they flow in the same direction as their equivalent message. So path tear messages flow downstream, and reserve tier messages flow upstream. And the purpose of these messages is to remove the resources that were allocated by their equivalent. So path tier messages are removing the resources allocated by path messages. Reserve tier messages are removing the resources that have been allocated by the reserve messages. And then we have finally error messages as well. So we have path error and reserve error. And these messages flow in the opposite direction. So path error messages are going to flow upstream, and reserve error messages are going to flow downstream. And they're there to indicate that there's been a problem processing or a problem allocating resources for the associated message type. And they're there to signal to the sending device that there's been a problem, and that device should back off and maybe try to attempt signaling at a later date. And this is a quick overview of RSVP signaling. In a previous video, we've seen how we can use RSVP to signal LSPs throughout a network. And RSVP can use the explicit route object to specify with great granularity where LSPs should be placed within a network. So it's easy to see how we could use this explicit route object to define specific paths for LSPs through our network. And this way we can have LSPs satisfying very tight criteria that our network demands. However, you can also see that just doing this via explicit route objects alone, that there could be a very high admin overhead. We are traffic engineering, but we are having to manually define the placement of every LSP that we want. And we're also having to manually define how the network reacts to failure. Because if a link fails, we then have to redefine what that ERO looks like. So this is obviously far from ideal if we want to place LSPs along certain paths within our network, but we want the admin overhead to be less, and we want the solution to be reactive to failure. So is there a better way to do this? Well, there is, and what we can do is we can instead deploy CSPF. So CSPF stands for Constrained Shortest Path First, and as the name would suggest, it's a modification of the SPF algorithm that you find in ISIS and OSPF. And instead here of defining EROs, what we're doing is we're advertising the current state of the network with more information than just link metric alone. Things like the amount of available bandwidth on a link, the type of service that a link is, whether a link can support the high-level prestige services alone that our network offers, or whether we can allow commodity services to form across that link. We can also advertise things like whether a link shares fate at layer 1 or layer 2, so we can have better diversity in our network. And with all these constraints advertised network-wide, we can then have our head-end routers, our ingress LSRs, perform dynamic calculations for LSP placements based on the constraints that have been advertised throughout the network and the constraints that we want these LSPs to fulfill. So with this said, let's have a look at Constrained Shortest Path First, CSPF, in a little bit more detail. So the first thing that we need to do is that we need to be advertising this extra information network-wide. And we do this through two slightly different extensions to OSPF and ISIS. If our main IGP is OSPF, we're using opaque LSAs to carry this additional constraint information. If we're using ISIS, we're carrying this additional information in extra TLVs. This traffic engineering support in ISIS is implicit. It's on by default. If you're using OSPF, you have to explicitly enable this traffic engineering support before you can support CSPF in an OSPF environment. So we have this extended IGP. The IGP continues to populate the standard link state database as it always did, with the router-to-router connectivity and link metric information. However, it's also populating a new data structure called the traffic engineering database, and it's pushing the same router-to-router and link metric information into the traffic engineering database. However, it's also populating this database with things like the available bandwidth on links, whether links share fate at layer 1 and layer 2, and the admin group or link affinity, so that the locally applied label to links that give them local significance within an organization. And so we have all of this extra information in this traffic engineering database, and we're going to have the CSPF algorithm, the modified shortest path first algorithm, run on this traffic engineering database. But first, we need to actually supply the CSPF algorithm with constraints. So this basically means we are defining in configuration on our head-end router, on our ingress LSR, the constraints that we want an LSP to fulfill. So that's things like the amount of bandwidth that a particular LSP is going to consume along its path from ingress to egress. And so we configure these constraints on the head-end device. We configure how we want our LSPs to be signaled throughout the network, and we push these constraints to CSPF. And CSPF is then going to try and find a path for an LSP with these specified user constraints from the traffic engineering database that has been populated by the extended IGP. And I've put a few of the steps that the CSPF algorithm takes up on the board to illustrate its functionality. This is by no means a complete list of the steps that CSPF takes, but it will hopefully illustrate the basics of how CSPF operates. So the first thing that CSPF does is it looks at the traffic engineering database and it removes any links from that database that do not satisfy the user constraints that we've specified for a given LSP. So that's things like links that don't have the amount of bandwidth available that the LSP is attempting to reserve, and also links that don't have the correct admin group. We can also specify explicit hops to CSPF, and if we had done that, the next step of the algorithm is that we iterate over trying to find the shortest path to all of those explicit hops. As one is satisfied, it's removed from the list, and we iterate through it until all of the hops have been removed from the list. And then once this is done, we try and find the shortest path that's satisfying all of the criteria. If we have equal paths, we then tie break on the available bandwidth ratio. So this means that we're preferring the end-to-end path that has the highest maximum available bandwidth ratio. Key thing to note here that we're talking about ratio, not explicit amount of bandwidth free. So 10 megs free on a 100 meg link, 10% availability, is better than 50 megs free on a 1 gig link, 5% availability. So this is how CSPF operates, and the end result being we've chosen a shortest path that satisfies all of our user constraints. And CSPF, generating this shortest path, produces an explicit route object listing all of the IPs from the head end to the tail end of this shortest path. And this explicit route object is then passed to RSVP for signaling. And then RSVP actually goes ahead and sets up that LSP that's going to satisfy this ERO, which has also been produced by CSPF, that's satisfying our user constraints that we supplied in configuration at the start of this process. This is a quick overview of CSPF. In a previous video, we talked about CSPF and how one of the constraints is that we can use locally significant labels on our interfaces to specify where LSPs should form within a network. So these locally significant labels are called admin groups in RSVP, sometimes also called link colors or link affinities. And what these are are ways that we can give local significance to our links within our network. We can label them appropriately, and we can have LSPs react to those labels. And this is probably best described with a few example use cases. So let's refer to the diagram on the right-hand side of the board. Say we have router 1, and he's going to establish several LSPs to router 5. And router 1 is a multi-service router. He's supporting a prestige voice service that has requirements to use very low latency links. And he's also supporting a commodity internet service that doesn't have low latency requirements, but has a high capacity requirement, needs to use links that have very high bandwidth. How are we going to give this service awareness to the downstream network so that we can have the downstream network correctly fulfill these differing service requirements that exist on router 1? Well, as you've guessed, we can do this with admin groups. So in this example here, we've coloured our high cost but also low latency links with the gold admin group, and we've coloured our commodity high capacity but also high latency links with the bronze admin group. And then on R1, we configure the LSPs associated with the voice service to include links that have the gold admin group and exclude links that have the bronze admin group. And for the commodity internet, we do the complete inverse of that. We're including links labelled bronze and we're excluding links labelled gold. And this way, we can then associate these different LSPs that are associated with different services to different physical paths in the network. So we can map physical connectivity to the appropriate service on the head-end router. And as I've mentioned, with these admin groups, you can either include or exclude, or use a combination of include and exclude when you're specifying which admin group you want an LSP to form on. So this imparting of service-specific awareness to an MPLS network is one use case of admin groups. Another use case of admin groups would be that you could have a admin group allocated for planned maintenance, and we have this down admin group here to illustrate this purpose. So ahead of a planned maintenance, you could label the link that you're going to be taking down with this down admin group. And prior to this, all of your LSPs network-wide have always been configured to exclude this down admin group. So when it comes time for the maintenance, all of your LSPs will have moved off this path because of the presence of the down admin group. So now this link is safe to take down for maintenance, and we can be sure that we're not going to be causing any end-to-end service issues when we're performing our maintenance on that link. How are we actually advertising these labels within the network, and how are we acting upon these label values? Well, let's have a talk about this theory now. So within the extended IGPs, when we're advertising information about links, we're advertising a 32-bit field, and this 32-bit field represents 32 possible admin groups. And then locally on each router, we give these 32 possible values a local significant name. Hence we give the value of 1 to gold, value of 2 to down, and the value of 3 to bronze. And you make this configuration consistent network-wide, and then you're able to configure LSPs to exclude these locally configured values appropriately. If you have a very highly complicated network and you need more than 32 possible different admin groups, then this is now possible due to fairly recent enhancements to RSVP. You can use the extended admin groups. And the extended admin groups allow the support of many millions of different admin group labels. So if you need more than 32 different admin groups, you need to use extended admin groups. And this is a quick overview of the use of admin groups within RSVP TE. In this video, we're going to take a look at primary and secondary paths for LSPs. So let's first imagine what happens in a typical failure scenario. So imagine we have this network deployed on the right-hand side of the board. We have an LSP running from R1 to R5, and this LSP is carrying prestige services, so we want to minimize downtime when any infrastructure that's carrying this LSP fails. Say this LSP is running on this northbound portion of this network, and one of the links that's carrying this LSP, say the link between R2 and R4, fails. So the first thing that happens is that the head-end router is notified of this failure through the sending of error and tear messages. Once the head-end is aware that this LSP is no longer functional, he starts to remove state for this LSP, and he starts to look in his TED database for an alternative path for this LSP. So he's rerunning a CSPF calculation on the TED database, and he's going to find an alternate path for this LSP, taking this southbound portion of the network. Once this path has been found, he then uses RSVP to signal that path. Once that new LSP has been signaled, we start forwarding traffic on that new path. So all the while all these steps are going on, traffic that wants to use this R1 to R5 LSP is down, and service degradation is happening. So what can we do to minimize the amount of downtime that this LSP would experience in a similar sort of failure scenario? Well, what if we can have a primary path for this LSP, and we can also pre-signal a secondary path for this LSP? So if this failure were to happen again, we still need to notify the head end of the failure, but as soon as that notification gets to the head end, we already have a pre-existing path that's already pre-signaled that we can immediately switch traffic into and restore service. And this is what primary and secondary paths in MPLS are for. And when we have a pre-signaled secondary path, we use the standby flag in configuration to make it pre-signaled rather than have to have it be signaled when the head end is notified to switch from primary to secondary. So this is all well and good, and it does dramatically reduce the amount of downtime, particularly if we have a very large geographic span of our network. When you configure primary and secondary paths in Junos, you can explicitly specify the paths that these LSPs need to take, but you can also let the router do the path computation for you. If you are configuring a primary and a secondary path, the router, with no extra configuration, is going to attempt to have the secondary path as diverse as possible from the primary path by automatically adding prohibitive metrics to the links that the primary path is taking. So this allows you to automatically have great diversity for your secondary path with minimal amount of configuration. There is a problem with this primary and secondary path approach though. You see here in this network that the primary and the secondary paths are diverse for the vast majority of the end-to-end path of the LSP. However, they are sharing the link between R4 and R5. In normal configuration, we are using fixed filter resource allocation, which means that these paths within the LSP are having new resourcing allocated for them under that LSP. So say that this LSP was using 600 megs of bandwidth, and these links are all 1 gig. The primary path of the LSP reserves 600 megs of bandwidth throughout the network. The secondary LSP is also going to try and reserve that 600 megs of bandwidth through the network, and that succeeds all the way up to this R4 to R5 link, whereas resource allocation is not possible here because we're looking to try and reserve 1.2 gigs of capacity on a 1 gig link. So the secondary LSP fails to establish. So in this case, what we need to do is we need to change the resource allocation from fixed filter to shared explicit by using the adaptive knob in the configuration. What this then means is that all paths underneath the same parent LSP share the same resourcing. So when the secondary LSP comes to reserve resources on the path through this network, we're only allocating that 600 meg once on the R4 to R5 link, so we are able to establish that secondary LSP. So this is the basics of primary and secondary LSPs. And as I mentioned earlier, the Junos operating system by default is going to try and find a diverse path for that secondary LSP. However, the Junos operating system, routers in general, only have awareness of layer 3 topology. So let's take a look at this example on the left-hand side of the board and see what the problems are with that when it comes to automatic diversity calculations. So say that we have a router R1 and he has an LSP running to router R3. And again, we want to have a primary and a secondary path. And you see that the R1 and R3, from the perspective of R1, are directly connected because it has two layer 3 links from R1 to R3. However, those links are running through a shared piece of infrastructure, a shared layer 2 switch in this example. As far as R1 is concerned, these links are completely diverse, so he is likely going to form the primary and the secondary LSP on these two links. And then if this switch were to fail, both the primary and the secondary LSP are going to be torn down at the same time. What would be better was if we have the primary path running through the switch, and if we have the secondary path running via R2. And we can do this in RSVP by making RSVP layer 1 and layer 2 topology aware by using a concept called shared resource link groups, or SRLGs. Now these are tags very similar to admin groups. In fact, extended admin groups use the SRLG functionality within RSVP. And what they allow us to do is to tag links and inform routers that these links belong to the same shared resource link group. So in this case, we can say this link 1 and link 2 belong to the same shared resource link group, i.e. they share fate because they pass through the same switch. And by using these tags, we're informing R1 that he should try and find the secondary path for an LSP that's running across this shared resource group through different links within the network. And that allows us to give this layer 1 and layer 2 awareness to RSVP so that we can have routers automatically use this information to find the most diverse paths for primary and secondary paths of LSPs through a network. In this video, we're going to take a look at RSVP fast reroute. So in a previous video, we saw how the use of primary and secondary paths for LSPs can improve the speed of convergence in an RSVP-enabled network. However, with primary and secondary LSPs, we're still waiting for the signaling to get back from the point of failure to the head-end router, the ingress LSR, to then switch onto that secondary LSP and restore service. So what would be better was if we could react at the point of failure and immediately route traffic around that failure point. And this is what we achieve with fast reroute. All we're doing here is that we're restoring service for a very short period of time at the point of failure, routing around that failure point. And we're using these detour paths or bypass paths that we're going to talk about in a little while to restore that service. All the while in the background, the same signalling that we've already talked about, that notifying the head end for him to rerun CSPF, is still going on. It's a key thing to note that with fast reroute, all we're doing is we're buying that little bit of extra time for the head end to find proper alternate paths. Fast reroute LSPs only tend to be used for sort of a couple of seconds before the head end finds a good permanent new path for that LSP to run over. So with that said, let's look at the two main flavors of fast reroute that we get within RSVP. The first is fast reroute detour, and this is what we have illustrated on the topmost side, the right hand side of the board. And so what we have here is we have the main LSP flowing probably from some router further upstream to some router further downstream. It's hitting router 1, and at router 1, what we're doing, and at every other router that this LSP is crossing, is if possible, we're also signaling, as well as the main LSP, we're signaling detour LSPs that are routing round points of infrastructure that this LSP is relying on. And these detour LSPs take alternate paths through the network to the end destination somewhere downstream of the network. And should, say, this R1 to R2 link fail, for a short period of time we route traffic onto the detour portion of the LSP to get that traffic down to the end destination. And this is all well and good. However, it does consume quite a lot of state in the downstream network. So the more favoured approach to fast reroute within RSVP is what I've illustrated on the bottom side of the board, which is the use of facility protection, or link and link node protection. And what we have here is we have an example LSP traversing R1, R2 and R3, and with facility protection, with link and node protection, what we have is we have bypass LSPs that are pre-signaled and routing round pieces of infrastructure that this LSP is traversing. For example, this bypass LSP here is protecting the link between R1 and R2. This bypass LSP here is protecting the link between R1 and R2, and it's also protecting R2 itself. So should R2 fail, what happens is that traffic from this LSP is temporarily tunneled through this bypass LSP to R3. If this LSP continued on downstream, this is what's called the merge point, where traffic would egress the bypass tunnel and then re-enter the main primary LSP. And this approach has the benefit that these bypass LSPs can be used to protect many thousands of normal LSPs routing through the network. All of the LSPs that are traversing the piece of infrastructure that the bypass LSPs are protecting can use them for protection. So you can see that this scales better than having this detour approach where every LSP that we have in the network has to have these branch points routing around the downstream points of failure. And this is quite extensively used in a lot of service provider networks today. So this was fast reroute protection within RSVP. Before we finish this video, it's worth just very quickly mentioning that today there are some protection mechanisms available in LDP as well. The main one being LFA, or loop-free alternates. And this will automatically in the background calculate alternate paths that your LDP traffic can take through your network. And it's going to give you fast reroute dynamics, much like these fast reroute dynamics are used with RSVP. One caveat with LFA, particularly in its most basic form, is that it doesn't give you complete coverage of all topologies where it's deployed, particularly if there are a heavy use of ring structures in your network. So if you're turning to LFA to protect your LDP network and you have the heavy use of ring structures, careful design is needed, and perhaps some more advanced LFA features are needed to get complete coverage protecting all of your infrastructure. And this is a quick overview of some of the different fast reroute techniques that are available for MPLS protocols. In this section, we're going to take a look at routing table integration for MPLS. So by default on a Juniper device, you're only going to be MPLS forwarding traffic to destinations that have been learnt through BGP. And let's explain why this is first off. So on the board here, you have the typical interaction of some example routing protocols and two main routing tables on a Juniper device. So you've got your IGPs populating the IPv4 internet table inet.0, and the preference for these protocols, so ISIS, we've got 15 here. There are other values as well, but let's just say 15 for now. And OSPF, again, there are other values, but let's just say 10 for now. These protocols are populating the inet.0 table, as you're probably already familiar. We also have the MPLS specific table of inet.3. So we have our MPLS label advertisement protocols, LDP and RSVP, populating inet.3 with the IP endpoints of the LSPs that these protocols have signaled. And LDP is populating with a preference of 9, and RSVP is populating with a route preference of 7. And to get traffic routing through an LSP, the IP endpoint of that LSP needs to be in the inet.3 routing table. So let's have a look now and see how BGP routes get MPLS forwarded. So we have a route in BGP, and that route has an associated next hop. We need to resolve this next hop. So this is a process particular to Juniper where we're building the forwarding table entry from this IP prefix. And what we're doing is we're looking up the next hop of this BGP route in both of these routing tables. This is this BGP IP resolution that I've mentioned here. So we're looking up the next hop of a BGP route in both the inet.0 table and the inet.3 table. And say this is a route that we've learnt from iBGP. The next hop of this route is going to be the loopback address of an iBGP speaker within our network. So this IP address is likely going to be advertised to us via an IGP. But we have MPLS enabled, so we also have label switch paths to this IP address. So they're appearing in inet.3 as well. So say that this is a ISIS enabled network. We have an ISIS route for this loopback address in inet.0. So we have a route preference of 15. So we have an RSVP LSP to this loopback address. So we have an RSVP route in inet.3 for this loopback address. We're consulting both tables here because we're doing BGP IP resolution, and we prefer the RSVP learnt route by virtue of its route preference, 7 beats 15. Therefore, in the forwarding table, we install the LSP route to the loopback address, so we MPLS forward traffic to the edge router that has that BGP route on it. What if we want IGP learnt destinations to be MPLS forwarded as well? Now, so by default, IGP route resolution is only going to be consulting the inet.0 table. So there's no possibility for us to be able to use these LDP or RSVP learnt destinations to forward traffic. Therefore, we're not going to be able to MPLS forward traffic to IGP alone learnt destinations. So there are some knobs that we can turn on on Juniper devices to alter this behavior. This is what we see here. So the first is the Traffic Engineering BGP IGP knob. What this does is it moves all the routes from inet.3 into the inet.0 table. So IGP route resolution is now going to consult inet.0, and we're going to have those LDP and RSVP routes in there. So we're then able to build forwarding table entries that make use of MPLS switching to these destinations. So this solves the problem, and it means that we get MPLS forwarded traffic for IGP learnt destinations. However, it does come with a problem. If we're using this network for multi-protocol BGP, so we have MPLS VPN, sort of layer 2 and layer 3 VPN routes learnt across our IBGP infrastructure, then routing for these destinations is going to fail. Multi-protocol BGP VPN route resolution only uses the inet.3 routing table. So if we've moved all of the routes from there to inet.0, this table is now empty, so we don't have anything to resolve these routes. So route resolution is going to fail for layer 3 VPNs, layer 2 VPNs. So we can't use this option in that case. Instead, what we could use is BGP IGP both ribs. So what this does is, instead of moving routes from inet.3 to inet.0, it copies routes. So the routes are left in inet.3 to support multi-protocol BGP VPN route resolution, and they're copied to inet.0 to facilitate IGP route resolution. And there is a final option called MPLS forwarding. So this is quite a complicated option, and it's seldom used in live networks. What essentially we're doing is that we're nominating the inet.0 table for routing, and we're nominating the inet.3 table for forwarding. And this was an overview of routing table integration with MPLS on Juniper devices.